In this problem, we'll go through another method towards using experimental data to calculate partial molar quantities. Specifically, we're going to go through an iterative method. And so in this problem statement, the premise is that there's some local bar that's sponsoring a contest where the contestants are supposed to mix equal volumes of ethanol and water together to make a final mixture that has a total volume of 100 centimeters cubed. All right, and so the idea is that you have equal volumes of ethanol and water, when added together, give you a final volume of 100 centimeters cubed. The contestants who are able to get closest to this win a plate of free food. And so in part A of the problem, what it asks us to do is derive an equation that describes, the volumes of pure ethanol and pure water, and when added together would give you some final volume V sub T. Okay? And the problem statement also tells us that the partial molar volumes for water and ethanol are given in figure 1 here. Okay? And where the y-axis, the x-axis is a mole fraction of ethanol, and the left-hand side here is the partial molar volume of water, and the right-hand side here, which corresponds to this curve, is a partial molar volume of ethanol. Okay? All right, and then part B just asks us to then use the equations from part A to calculate our VW and VWE needed in order to get a volume of 100 centimeters cubed. So based on the information in this problem statement, what I want you to do here is pause the video and sketch out a sort of schematic of the system. Okay, so based on the information in this problem statement, we could sketch out something that looks like this, where we have some mixture that's made up of water and ethanol, and the molar volume of pure water is here, and the molar volume of pure ethanol is here. Now, as we go through this problem, I'm going to call species 1 water and species 2 ethanol. Right? So that's a little bit backwards from the x-axis here, but I'll make sure to account for that. Okay? All right, and so in this problem statement, we want to basically add water and ethanol together in order to get a final volume of 100 centimeters cubed. And so we're going to have two sorts of constraints or two sorts of engineering constraints that we're going to have to deal with in order to accomplish this goal. The first constraint is that the total volume is just going to be equal to the volumes of water and the volume of ethanol in our system. The second constraint is that the volume of water in our system is going to be equal to the volume of ethanol as well. So that's straight from the problem statement. That's referring to this here. All right, and so based on these constraints, what we want to do for part A is develop an equation that describes the total volume in our system as a function of the volume of water and ethanol. All right, and so we know that in general, the volume of our system, of our mixture, is going to be equal to the summation of the partial molar volumes multiplied by the molar amounts of each of the different species. Right? So that sum has to equal 100 centimeters cubed. And we know that the total moles in our system are just going to be equal to N1 plus N2. All right? And so in order to get the total moles and we need these molar amounts. And we'll also use these molar amounts in our volume calculation as well. Now, to get N1, we know that we could actually get it from the volumes, right? Because we know that the molar amount is just going to be equal to the volumetric amount of species 1, the water, divided by its molar amount, right? Because this here has units of centimeter cubed, and this here has units of centimeter cubed per mole. So if you just divide the two, you're going to get moles left over. Similarly, N2 is going to be equal to this. All right, so we could describe our molar amounts in terms of volumes. So we could just plug that back into this summation here. So V total V is equal to N1 V1 bar plus N2 V2 bar. We'll now plug in for the moles. V1 over V1 molar, V1 bar plus V2 V2 molar, V2 bar. Okay? And from our engineering constraint, we know that V1 is equal to V2. Okay? And so we could actually just factor out the V1, and we get V1 bar over V1 molar plus V2 bar over V2 molar. Right? So all of this is going to be equal to V. Right? Now in the end, what we want to figure out is this V1 amount. Right? We want to figure out the amount of water we need to add into the system. And we know that based on our engineering constraint, the amount of water, the volume of water we add to our system needs to be equal to V2. Alright? And so, if we just solve for V1 here, we get the following relationship. Okay? Alright, so now we have our equation, and we could call this VT. We now have our equation that describes how the volumes of the water and the ethanol are related to VT. Okay? Alright, so we have our equation. Right? That's what Part A asked us to do. What Part B asked us to do is to actually calculate, these V1 and V2 values. All right? And so to do that, we know our V sub t value. Our target is 100 centimeters cubed. We know the values for pure the molar volume for pure water and the molar volume for pure ethanol. But the tricky thing here is these partial molar quantities, right? So V1 bar and V2 bar. Now these partial molar quantities, those are going to be a function of the composition of the mixture. And so if we go back to the problem statement, we have that figure that has, just to make this a little bit more clear, this is going to be V1 bar. This one's going to be V2 bar. Okay? Let me make that 2 better. Okay. All right, so that's what this plot is representing. Okay? And so to get these values, right, they're going to be a function of the x-ethanol mole fraction. And so to be able to get these values, we need to know what our mole fraction is. And then we would be able to pluck them off the chart. All right? But that's the issue here, right? We actually don't have any mole fractions at the moment. That's essentially what we want to figure out. All right? And so to vocalize this, so we know V, V1 molar, and V2 molar. But we don't know X1 or X2. Consequently, we can't just directly read off our V bar values. Look up V1 and V2. Okay? All right, so we don't know the X1 or X2 values ahead of time. All right? And so to overcome this issue, we're going to apply a different kind of strategy. So one that you may have seen in your computations class. And it's a strategy that we're going to use quite a bit in the last third of the course, when we start doing flash calculations and studying more in depth vapor-liquid equilibrium. All right? But this may be the first time we introduce it in the class. Okay? And so the approach we're going to follow is an iterative approach, or as older engineers like to call it, a guess and check approach. All right, and so that's the approach we're going to follow. All right, and so what I'm going to do now is sort of sketch out the steps involved in a guess and check approach. Okay? And so in a guess and check approach, what you do, since we don't know V1 bar, V2 bar, or X1 bar, and X1 and X2, what we're going to do is we're just going to make a guess for one of those parameters. All right? And so in our case, we'll say we're going to take an initial guess of our V1 amount. Okay? Right. And as far as, what a sensible guess would be, we'll just say, okay, it's going to be half the amount of V2. Or half the amount of the total V sub t. Okay? So we're going to just take that as an initial guess. And then based on that initial guess for V1, we're then going to calculate N1, N2, X1, and X2 just by using all the equations that we had set up in this section. Okay, specifically if we have a guess for V1 and we know V1 squiggly, we could get N1, and so on and so forth. So we'll calculate those values based on our guess. And then once we have guesses for X1 and X2, we'll use our X1 and X2 values to then help us look up values of V1 bar and V2 bar, okay, from this plot. Once we have V1 bar and V2 bar values, we could then return to our calculation here and then calculate a V1 value. So calculate a new V1 using that equation 1 that I marked off here. Okay? All right. So then we calculate this new V1 value. And what we do is we then just keep repeating the calculation until the V1s we calculate basically converge, or they don't change upon subsequent iterations. Okay? All right, so that's the premise of this sort of guess and check approach. And so what we're going to do is put it into motion. All right? So first, we'll start with what I call iteration 1. All right? And so, as I said, we got to make an initial guess for V1. And just based on the problem statement, we know that that's also going to be equal to V2. All right? And then as an initial guess, I suggested we just take V sub t divided by 2. So 100 divided by 2. So our initial guess is going to be 50 centimeters cubed. All right. Okay, so if our initial guess of V1 is 50 centimeters cubed, N1 is going to be V1 divided by V1 squiggly. So it's 50 centimeters cubed divided by 18 centimeters cubed per mole, 2.78 mole. All right? Then for N2, it's going to be 50 centimeter cubed divided by 58 centimeter cubed per mole, which is equal to 0.862 moles. Now that we have N1 and N2, we can calculate total N. And then once we have that total N, we could calculate both the X1 and X2 mole fractions, but because our plot is the mole fraction for ethanol, which in our setup we say is species 2, all we really need is x2. Okay? In fact, just to clear that up. Oh yeah, never mind. Yeah, so we're just only going to use x2 for our calculations. But you still can calculate x1 if you wanted to. Okay? So x2 is going to be 0.24, or 0.24. That's the mole fraction. Okay? So we now have this mole fraction of ethanol at 0.24. Now that we have this mole fraction, we can now go back to this figure and we could start to look up the values of V1 bar and V2 bar. Okay? So at x is equal to 0.24, that's going to be about here. So I'm going to draw this line here. Okay? All right, and so for water, we see that this line intersects here, and so water is on the left axis. And so we see that in this figure, when we read it off, we get a water value of about 17.7 centimeter cubed per mole. Okay? And for ethanol, where it intersects here, we get a value of about, actually, I think I went a little too far to the right. 0.24 is going to be this way, maybe a little bit closer to that intersection. Okay, so if we go, it intersects water here and ethanol, basically it's the same place. Okay, so for water, it's about 17.7 centimeter cubed per mole, and for ethanol, it's about 56. Okay, so we can now write those values down in our work. So at x2 is equal to 0.24. Our V1 bar is 17.7 centimeter cubed per mole. And V2 is equal to 56 centimeter cubed per mole. All right. Now that we have those V1 and V2 bar values, we can now calculate a new V1 and V2 using the equation we had previously. If we plug in, we should get a value of about 51.5 centimeter cubed. Okay? So we see that, initially we guessed that V1 and V2 were equal to 50 centimeters cubed, but by going through all these equations, we now have a new guess of 51.5. Using that new guess, we could then start our second iteration. So, next page. So, iteration 2. So now we're going to set V1 and V2 equal to what we estimated in that last step. Now we could calculate N1 again. Now we get 2.86 moles. So it's slightly higher than before. N2. Our total N goes N1 plus N2 equals 3.75 moles. All right. And once we have total N, we could get our x2. And once again, we get a value of about 0.24, right, if we go through that calculation. All right, and so since we basically got the same x2 value, we could read off these values off the plot again. So, as a result, our V1 bar value is going to be the same, and our V2 bar value is going to be the same. Right? And so if those are the same, if we go back into this equation, right, where now if everything on the right hand side is the same, that means the number we get out on the left hand side will also be the same. And so basically what we're seeing is that in 2 iterations, our V1 and our V2 values have converged. So in other words, same value as before. This tells us our solution has converged. Okay, all right. And so by going through this iterative process, we were able to estimate, the mole fractions and then also the partial molar quantities. Okay, and so this sort of iterative approach to solving the problem is something you're going to see not only later on in this class, you'll also see it later on in your other classes as well.